overshoot, we have a fast process with a Kp positive. Fast process coming first. Fast means that it's a short time constant. Is someone taking this for the entire class? Okay, great. So I will post the recordings of this. So we have a fast process coming first with the Kp positive, followed by a slow process, maybe T2 for Kp negative. So let's notice that in a fast process, for the slow process, it means T2 is the big one. So if T2 is big and Kp1 is positive, T2 and Kp is big, Kp1 is positive. This number is much bigger than this number, because T1 is small. Even though this is negative, this is positive, so this wins. So that's why T3 is positive. In this case, I start out with a fast process, T1 small, where Kp is negative, followed by a slow process, T2 is big, where Kp is positive. So T2 is big, Kp1 is negative. T2 is big, Kp1 is negative. This is big and negative. This is small and positive. So the negative wins. And in both cases, I'm assuming for this shape to hold that the sum is always positive. Now, that doesn't have to be. It could be the sum was negative and then things would switch. I just give you an example. So does that make that clear? Okay. So I don't know, maybe I'll call this Blackboard 4 because it's the second one. Okay. So let's look at recycle. Let's try to get a handle on recycle. And let me do a little diagram. What do I want this diagram? So, I have CSTR.
No, I just want to. Can you put my phone right here?
Where what comes out
Oh.
is this one. So what's the idea? I have a feed.
No,
I have a feed that is getting heated up by. I have a feed that's getting heated up by contact with some stream. It enters the reactor, and there's an exothermic reaction going on. Exothermal reaction. Exothermal reaction. So that tells me that what comes out of the reactor is hotter than what went in. So I have this hot stream, and instead of wasting it and dumping it in the river and killing all the fish, I recycle it and I contact it with the feed so that I can use that heat to heat up the feed, and then this might just be at normal temperature. So let's look at the energy, and we're interested in the energy now. Okay, so I need inputs and outputs. So this is, say, X. Well, actually, let me use notation consistent with both, so to make it slightly less confusing. No, we'll call it temperatures. Theta 2, theta 0, theta 3, theta 4. Okay, and what we'd like to do is we would like to turn this into a block diagram so we can use our G-tildes. So our goal, get the linear block diagram. For the system, and find G tilde of theta 4 prime tilde over theta 0 prime tilde. So we'd like to know how a change in theta 0 affects theta 4. So That's the goal. Is that the only goal possible? No, but that's the goal that we're using. All right, so the first thing I want to do is I want to focus first, part one, let's focus on the heat exchange. And we've done these heat exchangers before. We said rho v CV hat, I guess hat, not total, times d theta dt is equal to UA times, it's equal to Q. Well, actually, it's equal to, I've got the in minus out. So the in, no, actually, let's just, I've got this Q. And let's, when he said that was equal to UA times, theta 4 minus theta 0 plus theta 3 over 2. So if you remember, we had that approximation where really I should use that log mean like in unit ops, but in this class we approximated it by theta 4 minus theta 0, theta 3. Remember, theta 4 is the temperature in here, so it's well mixed. And let's just see if there's anything I left in. And then I have plus rho CP. So this is equal to plus rho CP times T in minus T out. Theta 0 minus theta. And let me just make sure I got the sign right before I answer your question. I just want to get the signs correct. Okay, so I've got theta 0 coming in, theta 3 going out. And then I've got theta 4 minus that. I think the signs are correct. Yeah?
I think I missed why theta 1
There is no theta 1 and theta 2 yet. Why did I number them 0, 3, and 4?
2. Yeah.
You'll see. I didn't say anything yet. Right now, I don't like 1 and 2. I don't like 1 and 2. I just want to go from 0 to 3 and 4. That's the only reason for now. Okay. So, and typically in the heat exchanger, we set this equal to 0. So we assume it's steady state. So now I have this thing equals this thing. And let's hope I didn't screw up these signs. So, and of course I have volumetric form. Okay, so I have theta 4, theta 4 minus theta 0 plus theta 3 over 2 is equal to rho CPV over UA. I probably want to do it the other way around. Do I want the UA or do I want it upside down? UA. Yes, I want the UA the other way around. So let's do it the other way around. I have theta, I'm going to move this to the other side of the equation. Theta 3 minus theta 0 is equal to UA over rho CPV. And I'm going to factor out the half, 2, times 2 theta 4 minus theta 0 minus theta 3. And this should be a theta, not a 0. I can't hear a word you're saying.
Is the 3 minus the 0?
Yes. Thank you. Thank you. Theta 3 minus theta 0. Okay. So I'm going to call this thing alpha so I don't have to carry it around all the time. And what I'd like to do is I'd like to solve for for theta 3 in terms of theta 0 and theta 4. And let's make these primes. By the usual method. Okay, so let's, again, I want to solve for theta 3. So let's bring theta 3 to the other side of the equation. So I've got theta 3 prime times 1 plus alpha. And that's equal to alpha times 2 theta 4 prime. And then I have plus theta 0 prime. And here I have a 1 plus alpha, 1 minus alpha, 1 minus alpha. Or I can rewrite this as theta 3 prime is equal to alpha over 1 plus alpha times 2 theta 4 prime plus 1 minus alpha over 1 plus alpha theta 0. And now I can Laplace transform, and I get that. And let's notice what I've done here. I've said that theta 3 prime, again, you don't have to worry about copying everything down. You'll have photos of this. Theta 3 prime tilde is something times theta 4 prime tilde plus something times theta 0 prime tilde. That tells me I can call this thing. Let's call that, say, I'm sorry?
I thought the alpha prime 0 is going to be gone since we have on the left side, the 3 minus the 0 is going to be.
Are you questioning the algebra?
Yeah.
Okay. So this is alpha. I add alpha theta 3 here, so that's 1 plus alpha. On the right, I've got the 2 theta 4. And here I have a minus alpha theta 0, minus alpha theta 0, and plus a theta 0. So that's 1 minus alpha theta 0. And then now I divide by 1 plus alpha. Okay, so I can call this, say, theta 1 prime tilde, and this I can call theta 2 prime tilde, because we discovered that I like the numbers 1 and 2. In other words, I can think of this as the sum of these two. How do I do a sum in a block diagram? Let's just make sure I got my numbers in the right order. 0, use this. How do I do a sum from block diagrams? Okay, I thought you were just a yoga. Okay, so that tells me that if I want sum here, I should just do, so this is theta 3 prime tilde, and then this would be theta 2 prime tilde, and this would be theta 1 prime tilde. So that's a representation of this. But I can call this thing G43, and I can call this thing G03. And then this thing is equal to G43 times theta 4 prime. And this thing is G03 times theta 1 prime. And now I've represented the heat exchanger. This is my block diagram of the heat exchanger. Yes. Yes, it should be theta 0. That's what happens when I write quickly. I make mistakes. Thank you. So, again, G times theta 0 prime gives me theta 1 prime. This G times theta 4 prime gives me theta 2 prime. And theta 1 prime plus theta 2 prime gives me theta 3 prime. So now we know why I kind of left out the 1 and 2. But now, I'm not just interested in the heat exchanger, I'm interested in the whole system. So let's do the whole system. So for the whole system, I've got the heat exchanger. So I've got theta 0 prime. That goes through G03 and comes out with theta 1 prime. I also have theta 4 prime. That goes through 3G43 and gives me theta 2 prime. And they combine to give me, we said, theta 3 prime. So I just copied this over. I just bent this leg a little differently. And it's theta 3 that goes into the reactor. So this goes into G of the reactor. G of the reactor. And what comes out of G of the reactor is theta 4. And there I have, this is for the entire system. And if that's for the entire system, then what I need to do is, now I want to calculate, remember my goal is to find theta 4 prime tilde over theta 0 prime tilde. So I'm going to start from here. And I know that theta 4 prime tilde is equal to, how do I relate that to theta 3 prime tilde? So you want to help me here? How do I write theta 4 prime tilde to theta 3 prime tilde? Starting here, I'm going to work backwards. So someone can see that? Volunteer? You don't want me to volunteer you, so you should volunteer. Remember, you've answered, I appreciate it, but you've answered questions. Someone hasn't answered yet. Yes, thank you. GR times theta tilde 3. But we already know what theta 3 prime tilde is. That's equal to this thing. It's equal to GR times G43 theta 2 prime tilde plus G03 times theta 1 prime tilde. So theta 3 is G03 theta 1 prime tilde plus G43 times theta 2 prime tilde. But what is theta 2 prime tilde? What is theta 1 prime tilde? What is theta 2 prime tilde in terms of theta 4 prime tilde? Volunteer? If no one raises their hand, I'm volunteering.
Is it G43 times theta 4, theta 4?
I'm sorry. Let's just make sure I got this right. Theta, I think I'm getting ahead of myself. This is G43 times theta 4. This is times theta 4. And this was G03 times theta 0. Actually, I have it already. I skip the step where this thing was theta 2 prime tilde. And this thing is theta 1. So what happened? So theta 3 prime tilde was theta 1 prime tilde plus theta 2 prime tilde. And theta 1 prime tilde was G03 theta 0 prime tilde. And theta 2 was G43 times theta 4 prime tilde. So I already done it for asking. Okay, so now let's notice that I've got a theta 4 prime on both sides of the equation. So I need to bring this to the other side of the equation, factor out the theta 4 prime, and divide. So I have theta 4 prime times 1 minus G43 theta 4 prime tilde is equal to GR G03 theta 0 prime tilde. Let's brought this to the other side. And I have theta 4 prime tilde is equal to GR G03 over 1 minus times theta 0 prime tilde. 1 minus GR, and this is factored out, G43. Where this is G over, now the G overall. And that tells me that G overall, which is defined as theta 4 prime tilde over theta 0 prime, is equal to GR G03 over 1 minus GR G43. And this was my diagram. So what do we conclude here? What we have here is the following. We have a block diagram for the linear approximation of the heat exchanger, and we have the G overall for this temperature as a function of this temperature, which changes in one or which changes in the other. And I want you to notice that if I didn't have any recycling, if I had no recycling, well, basically that would mean that G43 I set equal to 0. If I set G43 to 0, I get rid of the recycle. And if G43 is 0, then alpha becomes 0. If there's no recycle, if you like, alpha 0, because there's no UA. So it's probably easier if I just said alpha equals 0, because UA is 0. So there's no heat exchange. If there's no heat exchange, then alpha 0. If alpha 0, G43 is 0, and G03 is equal, so in that case, G43 is 0, and G03, if alpha 0 is just 1. So if I said G43 equal to 0, G03 equal to 1, I just have GR. So if I have no heat exchange, then G overall is just GR. Just get GR.
Yes.
On the other hand, when I do have heat exchange, G overall is GR G03 over 1 minus GR G43. Remember, the stability of the system depends on the zeros of the denominator. GR has a different denominator than this does. So I've gone from this denominator to this denominator. Moreover, what's happened? I have a system that's interacting because the temperature coming in here, 03, depends on the temperature going out. So it was like that tanks problem where Y3 influenced Y2. Here, theta 3 influences what comes out. And theta 4 influences what goes in. That's like Y4 influencing Y3. Y0 also influences it. So this is an interacting system. Whenever I have a recycle, I have an interacting system. And what we learned in the last hour was that in interacting, by the way, I really want to keep track of the attendance. Someone have a piece of paper? Because always, when I do this some semesters, I correlate the attendance to the grades. And I always find the people who don't show up to class are always at the bottom of the class, almost always. So I would like to do those. Can someone donate a paper? Also, the people who don't come to class will be the people who complain the most. So it's also good to have that correlation. Okay, so, all right. And what we learned was that the interacting, did you have a question? What we learned was that the interacting systems are more sluggish, they're slower. And so the interacting systems are more sluggish, we showed that in the first hour, and this is an interacting system. And the stability depends on this denominator as opposed to this denominator. So we see it's a different stability profile. And what we mentioned in earlier classes was that the systems with heat integration tend to be less stable because a fluctuation in one place affects more places. So more chances of things going wrong. Any questions on that? Yep.
Is it safe to say that whenever you have a move on the diagram, you will have correct systems?
Whenever I what?
Whenever you have a move.
A recycle. Yeah, that's an interaction. Yes. Yes, exactly. That's because the output is affecting the input. So if you like, that's like when I had the tanks, that's like a tank of a higher number, the output affecting the tank of a lower number. So by definition, that's an interacting system. Other questions? Okay, so in chemical engineering, we typically do staged operations. So in your unit ops class, I forget if it's unit ops 1 or unit ops 2, I always get confused. You have one class that's pipe flow and heat exchange, and the other one that's staged operations. So in the staged operations, you've got distillation, extraction, all these staged operations, which, frankly, that's